classification of data, whether it's my face or it's Naomi's face, will be done by separating the manifolds of the images that are my face and the images that are Naomi's face. So that's how it will tell whose face something is. The way that we separate them, we're going to do what are called continuous transformations. We're going to apply continuous functions that stretch this space, that squash this space in interesting ways. And then a neural net, a computational structure like a neural net, can do this. So I'm going to walk us through these with some concrete examples so that you see what we're talking about. So first of all, here's an example of real-world data that has been collapsed down onto a sphere and then rotated. So each of the dots is a different data item, sort of grouped together based on what kind of thing they are. And so you can see that even though you've got a three-dimensional structure, there's lots of one-dimensional structures here, little sort of strings in that sphere. Do you see that? And some of them are little blobs of things. This brown one in the middle is fascinating. If you look carefully, you'll see it's actually like an orange peel sort of structure in there. It's not just a blob, it's actually a two-dimensional thing that curls in and around on itself. So each of these manifolds, this is the nature of real data. When you take in all of the inputs, and in this case, as I say, we've collapsed it to 3 dimensions. Real data is messy like this. Like there's no easy way to say, here's how you separate the yellow things from all the other things. Like there's no easy rules about it. But it turns out that we will be able to build statistical models that indicate with high probability that it's a yellow thing as opposed to a brown thing, based on what we do to the data space. So each manifold, each of these substructures will represent a different entity, and we'll understand the data when we tease these entities apart. So this comes from lots and lots of dimensions. So we're going to go for a simpler thing. Handwritten digits, like just the digits 0 to 9 that you might write, when you're writing down a phone number, except nobody writes down phone numbers. So what we're going to do to get it into the computer is we're going to digitize the images, and on a 0 to 28, 0 to 27, and 0 to 27, so 28 by 28 pixels. So that is, every one of these digits will be grayscale on this. How many pixels are there? Well, I always have to look it up, 784, 28 by 28. So you can think of this as being an element in 784-dimensional space. It's one location in space that is that big. Is that making sense? Like there's 784 individual values. It's not like R cross R, two-dimensional space, XY coordinates, or even XYZ. It's X0, X1, X2, X3, X4, up to 784. So huge dimensional space. I mean, I don't know about you, but I find when I get beyond 3 dimensions, I've now trained myself to think in terms of 4-dimensional structures, and I can visualize 4-dimensional structures. 5 starts to get really dicey. By 6, I have to give up. I haven't figured out how to visualize 6-dimensional structures. I have no concept of what structures look like in 784 dimensions. And you might say, this is ridiculous, we only have 3 dimensions. We only have 3 physical dimensions. Mathematically, we can study thousands and thousands of dimensions. So data comes in very high dimensional space. So we've got these things, and you could imagine variants of 0, and it turns out that variants of 0 live near one another in this space. So what do we mean by that? Well, I've got a graph here of 8s. Here's a video running through lots of 8s. And this is their pixel values. And this is dimension 1 through to dimension 784. And one of the things that I notice as you run through this is this graph doesn't actually change all that much. I mean, sure, it jumps around a bit, but you see that it's kind of somehow fairly similar, even though the thing moves around. That is, all of those 8s somehow live quite near one another in this vast space. And it turns out that the 8s live near one another, the 0s all live near one another, the 2s all live near one another. So, really messy 8 there. So the manifold hypothesis would essentially say that all the variations in these handwritten digits, they form essentially 10 distinct manifolds, 10 little connected geometric areas within this very high dimensional space. And so now our job is to separate them. So how do we even think about it? So as I say, my brain's kind of small, I find lots of dimensions hard. So let's just go to 2-dimensional space. I can manage 2-dimensional space. So imagine that these are the 2 manifolds that I care about separating, the blue one and the red one. How do we separate them? Well, you know, one of them's blue, the other's red. But imagine that they're not conveniently colored in that way. Imagine that there are actually lots of data points dotted around here, and lots of data points dotted around here, and we want some way to be able to say what's going on with them. And we could try and do first wave stuff and define rules and segments and so on that divide that. But you know, who's to say that we're going to get it right? So it turns out that what we can do is take the data space itself and start stretching it and squashing it. If we do it in a particular way, as we stretch and squash it, we start to discover that we could do it in a way that actually teases those curves that used to be interwound and then no longer interbound, that they're separated. And now we've got the red ones at one side and the blue ones at the other side, and we could draw a line and say, I'm going to consider everything on this side of the line as being a red data point, and everything on this side of the line as being a blue data point. And it's really cool, just by doing stretching and squashing, you're able to do that to the data space, and that moves the data apart in such a way that you can draw these clean lines and say, this is one kind of data, this is another kind of data. But you might say, hey, I can see that, but what if I've got something in the middle that is completely surrounded by something else? Like this, for example. No amount of stretching and squashing of this will move this bullseye outside of the rest of the picture. Well, if you limit yourself to 2 dimensions, that's true. But if you add an extra dimension and start stretching it that way, then indeed you can cleanly separate it. So even though we started out with a vast number of dimensions, we may actually add more dimensions in order to give us more flexibility in stretching and squashing to be able to separate the stuff that otherwise would actually be entirely contained by other things. So it's a really cool idea, and what's astonishing is that we now have computing techniques to do this. And neural nets, and I suspect everybody's heard of neural nets. Neural nets are a way of doing this, of being able to stretch and squash data. So here's the big secret about neural nets. People talk about they're modeled on the human brain and consciousness and all sorts of things like that. Neural nets are just spreadsheets. That's all they are. They're just fancy spreadsheets where you have a sheet where the data comes in, and then you do a bunch of calculations, you get another sheet of the data, and you have a bunch of calculations and you have another sheet of the data, and a bunch of calculations and you have another sheet of the data, and you may go on maybe 20 sheets, and at the end, you've got your answers. And what each of these layers will do is a step of stretching and squashing, stretching and squashing, stretching and squashing, in such a way that they separate it. Now there is magic here in that the way that you stretch and squash will be carefully tuned to your problem. Like there's a lot of work figuring out how to stretch and squash. But in terms of the mechanics of it, they're just spreadsheets. There's nothing sort of mystical about it. And so the way that you do this is each of these cells, I put it in Excel language really to emphasize it. There's a function in Excel called sum product. Take a bunch of weights, take the inputs, the value inputs from the previous layer. This calculation, it's called the inner product in vectors. And then you'll have some function. The pos function just says if it's less than 0, get rid of it and just call it 0. So it squashes everything that's negative to 0 and it leaves the positive stuff unchanged. So it turns out that's a pretty good function to use. So as I say, each layer transforms and squashes the space. When you have inputs, you compute it all the way up. When you're training, what you do is you compute it all the way up and then you realize, that answer's way off. And so you then take the distance that you are from the thing that you're trying to do, and you push it back to adjust your weights. And so hopefully you'll get a bit closer to it. And I'll talk about that in a minute. That's where calculus comes into it. So the key challenge is to learn these weight parameters from the example data. So I want to talk about two things. First of all, what's going on here with this sum product thing. So here's one touch into mathematics. It's just vector calculations. So those of you who've done stuff with vectors or matrices, that kind of world, this is the world that you're in. So much of the power of the modern AI comes just from doing matrix calculations. You may have heard of TensorFlow coming out of Google. TensorFlow is a powerful machine for doing vector calculations and things related to vector calculations. So I'm not going to teach you matrices, but I'll just give you an idea. The way that you do this calculation is you take this row and this column, and you do the multiplication piece by piece, x1 times w1, or w1 times x1, w times these two, the w3 times x3, and w4 times x4. You add those up. And then at the end, we'll add the corresponding first row of this, the blue B. And that's what we get out here. And then we do the same with the second row. We take this row and multiply it by the column, piece by piece, and you get this term and the third. And so that's actually related, very closely related to what's going on in each of the things. This would be this is how you calculate this, this A1. You calculate A2 by the green and A3 by the brown. So you do this vector arithmetic, and then just take this result and you squash it with the pos function. If it's negative, just turn it to 0. If it's positive, leave it as it is. That is a cell in a neural net. That's all that's going on. As I say, you do need to tune these weights here, and you do need to tune the B. But that's really the only interesting stuff going on. So how do you do the tuning? There, you use calculus. So I'm just showing you it in two-dimensional. In reality, in neural nets, you need to do it in hundreds of dimensions, calculus in hundreds of dimensions. So you don't do it with your paper and pen, you write a software that does it. But there's a technique. Who's come across the Newton-Raphson technique? Have any of you come across this? Okay. So this is a technique which is, I've got a curve here, and I want to find where does this curve cross the axis. And so what you do is you start out at a place, and you draw the tangent to it. And that tells you to come to here. And then here you draw the tangent here. Here you draw the tangent to it. And you see I'm sort of getting closer and closer to this point. And Newton-Raphson says, keep looking at the curve, do the calculus on it to find out how steep the curve is at that point. Follow that down to the axis, and use that to then the next place, and just keep iterating. And it's a pretty good way of finding routes to functions where you don't know where they're going to cross the thing. So in Newton-Raphson, calculating the tangent to a curve shows you how to find the route. In neural nets, calculating the tangent shows you how you need to move the weights to get a bit closer to what you're trying to do in the stretching and the squashing. And so studying calculus is the thing that lets you understand this is now how the thing learns. It's a technique called back propagation. And it's a very rich, very powerful method. So you need to know that how to do differential. And as I say, you end up actually doing it in multi-dimensions, not just in one dimension. So vectors, matrices, yay. Calculus, yay. These things are very relevant to what we're doing. So when you actually build a neural net, something that can operate on this data, you might take substructures which have been trained to learn something, maybe the notion of a vertical line here, or the notion of a loop, or something like that. And then they get reduced by subsampling down to